Welcome to the lecture 27 of Physics 10 in 30 lectures. We wrap up special relativity in this lecture, covering the remainder of chapter 13. In the first two lecture sections, we derived the two special relativistic effects that, when taken together, fully explain the null result seen in the Michelson-Morley experiment. That is, time dilation and length contraction. The third lecture section here is a follow-on discussion that clarifies our use of the term observe, which was mentioned in a couple earlier lectures. Then we have a number sense exercise that is trying to build some intuition around the two factors that commonly occur in relativistic expressions. The first is gamma, also called Lorentz factor, and the second is beta, which is just speed, expressed as a fraction of speed of light. Then we cover some aspects of relativistic momentum and energy. The last lecture section goes over calculation questions from the special relativity chapter. Most of the sections in this lecture set are borrowed lecture videos from Physics 4C, although hopefully with not too much math and enough concept-oriented content. For the lectures that are old Physics 10 lectures, for example, Chapter 13 homework questions, please note that there has been a general shift in chapter and section numbers from the old CNX platform to LibreText. For example, when you see Chapter 14, Section 14.3, covering length contraction, that is our current Chapter 13, Section 13.4, covering length contraction. Now, we look at the derivation of time dilation.
Welcome back. So time dilation is the first consequence of this postulate of special relativity that I want to explore. So this is the thought experiment. Imagine you built a clock that operates this way. So you have a clock that operates by bouncing light back and forth between two mirrors. And so I have one mirror here, I have another mirror here, and if these two mirrors are separated by distance L, then when I have a light beam or pulse here, bounces up, bounces from here, comes down, then I can use that round trip as my ticking of a clock. Or I guess, let me use the round trip. So as it goes up, comes down, when it comes down here, then some amount of time has passed. That amount of time t should be equal to 2L divided by c. Good? I feel like this is particularly nice clock because we've been just told the speed of light is constant at c. So if I can keep this length stable, then c is guaranteed to be the same, then it'll keep the same time no matter what happens. Now, we want to explore what happens as this clock is moving. And we want to be careful in the specification here. I want to specify that this clock is moving in a direction that's perpendicular to this axis. So it's moving in a direction that's perpendicular. So it's let's imagine that the clock. Imagine that this clock is moving with the speed v in a direction perpendicular to the direction that the clock is oriented in. Yeah? So if you are an observer A, staying with the clock, then nothing will change. That's the principle of relativity, right? So whether this reference frame is moving or is stationary, none of them makes a difference. From the person who's staying with the clock, nothing about the clock has changed. So I want to give it a special name. Let me call that proper time. So this time, let me call that, use a special letter. Greek, lowercase tau, to indicate this time. This is what we are going to call proper time. There's one special proper time for every object. Like my own proper time is proper time of the time kept by whatever reference frame I was in. Or like proper time of a train that's moving is the time kept in the reference frame where the train was stationary. So whoever's moving in the train. So when we call this proper time, then what we want to look at is how does this clock look from the perspective of observer B. So from the perspective of observer B, who's sitting out here watching the clock move, does it still take the same amount of time for this light to bounce from one mirror to the other mirror and then come back? So from the perspective of B, are these two mirrors staying stationary? No, they are moving, right? So as this light reaches here, this mirror actually moves over here, right? And in the amount of time for the light to come back, this bottom mirror has moved even more to over here. Okay? So the path of the light for observer B should look something like this. So this is the path of the light that the observer B sees. Okay? And that's what he observes. And let's see how much time, at what time t, the light comes back to this mirror. Now, for observer A, who stayed with the clock, so if I'm drawing everything, so observer A was here when the light hit there, and observer A is here when the light comes back. This same amount of time would have passed for observer A. So we are looking at, for observer B, how much time passed? Well, I think I have all the diagram. I think I can figure out how much distance all this is. And how fast is light moving for observer B?
C.
Yeah, C, because that's the second postulate of special relativity. So I can calculate how much time this is. Let's do that and see how much that actually is. So I guess I need to first figure out the distance that the light has to travel in the reference frame of B. So this is an assertion that I'll need to make without spending too much effort trying to prove it. I think this distance is going to remain the same. It's the distance that's perpendicular to the direction of motion, and that in that direction, the length is not going to change. Good? Okay, as long as you believe that, we'll move on. So this height will remain at length L. And I can come back and double check this when we have introduced Lorentz transformation. It's easier for me that way. So I need to know the length of this side. Let me call that delta x. Then this is a right triangle. I can figure out the hypotenuse. The hypotenuse should be square root of L squared plus delta x squared. So I need an expression for delta x. How far did the mirror travel in half the amount of time for the round trip? Can I use this expression? Not quite, right? Because this is not the time for this. This is the time for this. So I have to actually leave this as an algebraic expression, that this delta x is equal to speed times and some expression of this unknown time. So half this total amount of time. So t over 2. Yeah? And then return trip is exactly the same. So let me write down this algebraic expression and see if I can solve it for t. Okay? So the algebraic expression is the time of travel is equal to the distance. That would be twice this distance, square root of L squared plus delta x squared, which is the v squared t squared over 4. Distance traveled divided by speed. What's the speed? C. Speed of light is always c. By the way, that's one easy answer you can always get when we do special relativity. No matter what the situation tells you, speed of light is always c. That's one of your postulates. Even when it doesn't make sense, you know it's at least correct. Speed of light in vacuum is always c. I mean, you know, I do want you to make sense of it, but that's at least it's like a mantra. All right, so I have that. So time of travel would be t. So all of this is equal to t. And if this is beginning to look familiar, it's because it is. It's like what we did before. I have t on both sides of this expression, so I'm not done yet. I have to solve it for t. So let me solve it for t. Square both sides. So I have 4 over c squared times this, L squared plus v squared t squared over 4 is equal to t squared. Collect like terms. Let me go step by step. Distribute this. So you have 4L squared over c squared. 4L squared over c squared plus 4's cancel. So I have v squared over c squared times t squared is equal to t squared. Now I can collect the like terms on the same side. So moving this over here, I get minus v squared over c squared t squared. That's equal to this. Factor out t squared, I get 1 minus v squared over c squared times t squared. All right, I'm going to solve for t in one single step. Everyone okay with that? Okay, let me do that. T is equal to square root of this. So 2L divided by c divided by this. Divided by square root of 1 minus v squared over c squared. Seems correct to everyone? Yes? Yeah. And let me introduce a new notation. So as we are going through special relativity, you are going to see this factor a lot. This factor of 1 over square root of 1 minus v squared over c squared. It just occurs so many times that if I had to write it down every single time I saw it, my hand will get tired. So there's, we call it gamma factor or Lorentz factor. We introduce this symbol, gamma, Greek letter, is equal to 1 over square root of 1 minus v squared over c squared. So standard notation for special relativity. It saves a lot of writing. So in terms of that, this t is equal to 2L over c times gamma. Or let's see, I see 2L over c was this proper type. So this is what we can say. This amount of time it takes for the light to come back, t is equal to gamma times the proper time, tau. And this is the statement of time dilation. Does anyone see why we call it time dilation? Like everyone here knows what dilation means, right? Making things longer. Why are we calling this time dilation?
Because gamma is always greater than 1.
Yeah, gamma is always greater than 1. That's actually a good thing to note. Thank you, Gauger. Because, you know, gamma is this. This number, so V, we are going to, is this the right time to address it? So V is never going to be greater than C. You can see here that you run into some serious issues if V was ever greater than C. right? I think it's easier to say why that would be the case after we talked about relativistic energy and momentum. So we'll save that for next week. But V is always going to be smaller than C, which means 1 minus some positive number, square root. So this will always be smaller than 1, which means gamma will be always bigger than 1. So that's a good fact to know. Gamma is always greater than 1. And since you are multiplying the time kept by the clock itself in its own reference frame, multiplied by gamma, number greater than 1, this t is always going to be greater than the proper time. So we call, here's the thing. With the easy questions in special relativity, the most common mistake people make is forgetting which side something should be on. Like, is it tau equals gamma t, or is it t equals gamma tau? So to avoid the confusion, this is a helpful phrase to know. Moving clocks are slow. That's the English phrasing of time dilation. And this is the mathematical expression of moving clocks being slow. And this is what I mean by moving clocks are slow. So you see how fast this clock is going, 1 second, and imagine comparing against your own watch. If this clock is moving past you at some speed comparable to the speed of light, in the time it takes for this clock to count down 1 second, your own watch will count to something greater than 1 second. So this is slow. Yeah. So that's time dilation. So not that complicated. Yeah. But it is a bit unintuitive. And I guess what we'll skip in the interest time, you can read about it in your textbook. So 5.3. Your textbook does give you some examples of time dilation. And the most, best known is measurement of the lifetime of muon. Muon is an unstable particle discovered in the 1920s, 30s, early 20th century. And the interesting thing about this is, so it has a very short lifetime. And if you are assuming non-relativistic mechanics, then that's not enough time for it to ever reach Earth from upper atmosphere where it's produced. But because of time dilation, enough of them reach us to actually measure things. So you can read about that in the textbook. So that's time dilation. It's maybe not what you would have guessed, but once you drive it following these steps, it makes sense, right? Once you believe this, then you can believe that this bouncing back and forth of light somehow takes longer as this clock is moving past you. Okay? Then the second effect that I think we do have enough time for is something called length contraction, or sometimes we call it Lorentz contraction, after the guy who originally derived that expression. And I guess this is probably the good setup to use. In this, let me erase a bunch of stuff that was not correct. So once again, there's no such thing as an ether wind. So let me erase that. So no ether wind. And speed of light doesn't change as it's traveling. So, let me just make up some space here. And we'll use this setup for, so I want to actually use this Michelson-Morley apparatus to derive the second expression about length contraction. So here's the thing. Let's see. So this is what I want to be able to enforce. This is trying to make our theories so that it agrees with the experimental result that no shift of interference fringe was seen. There's no apparent difference in time of round trip this way and round trip this way when this entire apparatus, let me erase these two. When this entire apparatus is moving this way with the speed v. Good? Yeah. Just for reference, from what I got confused with earlier. Once you say apparatus is moving that way, the ether wind is going the other way. Good. Okay. So let's just say what you will find is if we simply say that so this portion of the arm acts like this clock that we just derived. So if while it's at rest, if it took this round trip time of tau is equal to 2d over c, then as this is moving, the round trip time of this will take more time by this factor gamma. So instead of this tau, as it's moving at speed v, the amount of time it takes will be gamma times tau. Now, this is what I want to enforce. I want to enforce that the round trip time of along this arm to take the same amount of time as this. So that when they come back, recombine here, then there shouldn't be any interference fringe because they all come back at the same time. Okay? So let's try to figure that out. So I'm going to stay in my own, I guess. So let me set up my observers this way. A is the observer who's traveling with my Michelson interferometer. B is the observer who stays here and just looks at things passing by. And from the perspective of B, let me erase this because this was the ether wind stuff. From the perspective of B, this is how things appear. Let me draw the things on the top, which is just a copy of this. So from the perspective of B, as the light travels up, the entire apparatus moves over. So this moves over here. This moves over here. Light hits here. And by the time light comes back, this whole thing moves over here. And light comes back here. And after the light, let me draw this V up here. So by the time light gets to this here, and it bounces back this way. Good? All right. Let's see. All right, that seems okay, right? That's what B would see here. Now, let me be careful here. So I'm not going to try to do any comparison at these 2 points. So for A, these 2 events, call it C and D, they happen at the same time. But I have a nagging suspicion that for B, it probably won't happen at the same time because it's 2 events separated by some distance, like with the train example. So I'm going to wait until those 2 lights come back to the same point to compare them. So when they're happening at the same point in space and time, then I'm reasonably sure that it'll happen simultaneously. It's like, when this ball is dropping and like same ball dropping at the same point, well, it's going to happen at the same time with itself, no matter in what reference frame you're looking at it. So let me do the calculation. So I know the round trip time for this. Round trip time for the upper arm is T is equal to gamma times, call it 2D over C. That's what we did with the time dilation. That's kind of why we had to do the time dilation first. And let's try to figure out how much time this round trip should take. And we will say that whatever round trip time this takes must be equal to this. Okay? So let's see. I guess I need to figure out some geometry. So in the time that the light reaches here, let me call that T1. So this happens at time T1. The mirror moves by some distance. And that distance should be V times T1. Seems reasonable? Okay. And so that's not it. I mean, that's not the total time. There's the return time. So in the time that, let me call the amount of time or the time stamp at which light reaches here, let me call that T2. So this T2 is from 0 all the way to this moment in time. This apparatus has moved this distance. This distance here. So that must be speed v times T2. Good? All right, I think that's all the geometry I need to figure this out. Right? So, all right, the total travel time, let me call it, I guess I can call it T. It should be the same as this. So let me, total travel time T is equal to the time, I guess that should just be T2. So, T2. And let me rewrite it this way. It's T1 plus T2 minus T1. Okay? And I can figure out T1 based on geometry. So at time T1, this has happened. The apparatus moved forward by this distance, or the mirror moved forward by the distance, and the light, which is our measuring stick for a lot of things, light has traveled the distance of d plus this. So let me say, so light has traveled d plus vt1. That's the distance that the light travels. So that's the distance. So that's equal to speed of light, c, times t1. Distance light traveled, distance light traveled. Okay? And I just want to warn you, in case I run out of time, we are going to get a little bit of contradiction. And when we run into that, we'll have to make a little correction. Okay? So, all right, so let's keep going. So I can solve this for T1. In fact, let's do that now. I'm not making any, okay. So if I solve for T1, T1 is equal to, move this over, so C minus V divided out. So T1 should be D divided by C minus V. Everyone good? Okay. And I can figure out T2 minus T1 as well. So the light is starting from this point. So it's traveling this and the distance of the this d plus v t1 minus this. So the distance that the light is traveling, that is this distance here. That's so this whole thing, d plus v t1 minus this bit here, v times t2. Good? And that should be equal to speed of light times t2. Notice how I'm using the same speed of light for both portions of round trip. It's, what is it because of? Yeah, second postulate of special relativity. So, if anything else is confusing, at least this, you can get speed of light is constant at c. Like, once again, I hope everyone eventually has an understanding of what that really means, but at least you know the correct answer, and you can understand it later, if necessary. Okay, so let me, wait, C times, not T2, it's a T2 minus T1 is the actual amount of time that the light spends. Good? All right. Oh, actually, let me rewrite this way. I think this will make my algebra a little bit easier. D minus v times t2 minus t1. Good. That's the left-hand side. So that means I can move this over. So I have actually c plus v. And when I divide it out, this is what I get for t2 minus t1. t2 minus t1 is equal to d divided by c plus v. Good? Okay. Let's plug these in, these two expressions, into up here and see what we get. I'm just going to move back here and write those expressions down. So total time t is equal to that d divided by c minus v plus this, plus d divided by c plus v. Let me combine the fractions. So when you combine the fractions, you get, so product of these two, c squared minus v squared, like you saw before. Okay, let me factor out d times, so c plus v plus c minus v. V's cancel out like before. I have 2c. So you end up with, this is equal to 2d times c over c squared minus v squared. Let me do a little bit of factoring that similar to what I did before. I'm going to factor out a factor of c on the denominator that doesn't really exist. So it's like, so let me do it in two steps. Multiply top and bottom of this fraction by 1 over c. That makes the numerator 1 and the denominator c minus v squared over c, right? And I'm going to factor out this c from the denominator. Then I get this c here. So this turns into 1. This doesn't really have a factor of c, but I can still factor out a c by turning this into square. Okay? So this becomes 1. So with all those corrections, this is what it is. 2d over c times 1 over 1 minus v squared over c squared. That looks familiar, right? That's gamma squared. So let me just do that. So this is equal to gamma squared. And this is where you run into a little bit of contradiction. This is the expression we are trying to get to. The total time of travel is gamma times 2d over c. I have total time of travel is 2d over c. All right, so far so good. But I have gamma squared. What did I do wrong? So let me save a little bit of time. Math-wise, I didn't do anything wrong. My algebra was fine. So what it is this d turns out to change. For us to be able to enforce this experimental requirement that these two light beams arrive here at the same time, turns out the only way to make that true is by allowing this length to change. It's such an unintuitive thing. It's like somebody telling you that this ruler is 30 centimeters long, but when it's zooming by you, it's going to be shorter than 30 centimeters. If it's moving at, I don't know the actual remember numbers. Let's say it's moving at 3/4 of speed of light, then instead of 30 centimeters, it's 15 centimeters or something like that. But that's the only way to make this consistent. Make this consistent with this and still not abandon the second postulate of special relativity. So you know what Sherlock Holmes said, once you eliminate the impossible, whatever remains, however improbable must be true, that's that thing. So what no law of physics tells you is that this length must be the same in all inertial reference frames. That's what our intuition says it is, But I told you from the beginning, your intuition is wrong. And there's no law of physics that says that the length does not change when you are in different inertial reference frames. So that's what I'm going to do. So let me make this correction. Wherever I had d before, it's going to become d prime, new length. And I'm going to make that new length whatever it needs to be, so that this expression will be equal to 2d over c times gamma. That's what it must be equal to. So let me, so this is the d I'm going to keep as d. So let me track down all the other d's. That's d prime, 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 prime. I guess that's all I have to do. I mean, I can prime all these, but it's implied. All right. So let's figure out what this d prime is. I can cancel out 2c, 2c. I can cancel out one factor of gamma. So I get d prime. So that's the length of this arm from the perspective of B. D prime is equal to d. So let me give it this d a name. The same way I gave the name for the time kept by the clock in its own reference frame, I can call this d proper length. It's the length of whatever object it is in its own reference frame. So the proper length of this ruler is 30 centimeters, no matter what reference frame you are in, because when I say proper length, I mean the length measured in its own reference frame. Okay, so that's the proper length. So d prime is equal to this proper length divided by gamma. Okay? So that must be true, because I have laws of physics constraining what I can do. I have experiment telling me that these two light beams must arrive at the same time. And I have a second postulate of special relativity that tells me speed of light cannot change on return trip. The only thing I can change is this. So that's going to change. Okay? So this is what we call length contraction, or Lorentz contraction. So this is length contraction. And let me just end with length contraction. For the sake of symmetry, let me end with the same phrase or similar phrase as what we had for time dilation. For length contraction, we say moving rulers are short. Moving rulers are short. Good? Well, let me give you a quick preview of what we are getting to on Thursday. And I want to explain a little bit of language that I'm going to be using while we are in special relativity. It's a shorthand to avoid having to do a lot of tedious clarification over and over. It's the use of one special vocabulary, observation. So I mean, in everyday English, the word see and observe means the same thing. You observe what you see. But I'm going to reserve this word observation in special relativity to mean something that's entirely different from seeing. So let me put it this way. How many of you here have some sense of how far away stars are? Really far away, right? Do you know what the closest star that's not our sun is? How far away it is? No, it's not that far. In terms of light years, it's actually pretty close. Light years are a very reasonable unit of measurement for astronomical things. Alpha Centauri, how far away is it? No one has them memorized? No one here is an astronomy major? I think 3.4, some like 3 or 4 light years away. So let me introduce a diagram that I'm going to be leaning on a lot, especially as we introduce the tools we are going to introduce on Thursday. And let me try to explain this distinction between seeing and observing in the way I'm using the word, in special relativity. I'm actually borrowing this from a popular upper division textbook author, Griffith. he wrote a textbook for, I guess, arts majors called Revolutions in 20th Century Physics that actually explains conceptual ideas even better than a lot of more rigorous textbooks do. And so this is the distinction between observing and seeing. And once again, I'm just trying to clarify the new strange definition I'm going to be using. It's a shorthand so that I don't have to keep reminding you that we have to make this correction every single time. So I'm going to, let me describe this distinction using something called the space-time diagram. So in space-time diagram, what you do is you illustrate motion in one-dimensional. So if you're drawing this in 2 dimensions, motion has to be one-dimensional motion, and passage of time in its own axis. So you do plot something with an axis like this. The position along the horizontal axis, trying to remember the conventions. Time along the vertical axis. Yep. So let me ask you this somewhat inane question. So imagine this, it's night, so you can see the night sky, and Alpha Centauri. I don't know what constellation that's in. Let me, so it's winter, so you can, when it's at night, you can see the winter triangle. There's Sirius, which is one of the brighter stars. Let's just say Sirius is, I don't know, 10 light years away. I don't know the exact number. So let me ask you this question. Can you, let's see. 2 separate questions. One, is it possible to see light emitted from Sirius right now? Why not?
Because the light needs time to travel.
Light needs time to travel. A different question is, can you observe light emitted by Sirius right now? And I'll tell you the answer is yes, with a very convoluted definition of the phrase observe. So let me illustrate it on this diagram here. So on the space-time diagram, this is how you might illustrate sort of Earth, Sirius, and light from Sirius, all that stuff. So let's say this is where Earth is. And I can actually plot the trajectory of the Earth on this space-time diagram. I'm going to use Earth's frame, which means Earth starts at position x equals 0. And it remains at position x equals 0 for all time, meaning it'll just stay here. It's kind of boring. Good? Yes? And for the sake of this discussion, let's say Sirius is at relative, like stationary relative velocity between Earth and Sirius is 0, which I'm pretty sure is not true, but let's just say it is. So Sirius is out here at 10 light years away. And the trajectory of Sirius would look like this. And these are all the different moments in time for Sirius. So when I talk about light emitted by Sirius, it would be, well, this light here. Light being emitted at this moment right now, simultaneous with when I say the word phrase right now. And it takes time for this light to travel. It'll take this light 10 years to get to us. So it'll take this light 10 years to get to us. So this is our 10-year mark. The light will finally reach us and we'll be able to see it. So now 10 years from now, when we finally see that light, will our astronomers think that that light from Sirius, that's what's going on with the Sirius star right now? No, our astronomers are not stupid. They are smart. They know how to correct for the travel time of light. And this is the sense in which I'm always going to use the word observe. When I say the word observe, we have already corrected for this travel time of light. Because I want to assume that our observers, A and B, I want to assume that they are smart. They know how to make these trivial adjustments, right? Like like all of you are smart, you know how to make that adjustment, and I'm making the same assumption for A and B. They know how to make those adjustments. So when our astronomers see the light from Sirius 10 years from now, they know that that's the light that was emitted right now, not 10 years later. So that's why I can say, so when I say observe the light right now, no, it does have to wait 10 years for me to actually make that observation, draw that reconstructed picture. So that's the sense in which we are going to use the word observe. And here's really the reason I'm going through all this painstaking detail to distinguishing between these two. I want to draw attention to how I phrased these two phrases. Moving clocks are slow, moving rulers are short. I didn't say moving clocks appear slow. No, moving clocks are actually slow. This is how we observe moving clocks. We have made all the trivial adjustments that can be made. After having done all of that, there's a real physical effect remaining, meaning moving clocks are slow. And the same thing with the rulers. Actually, with the moving clocks, it's kind of easy. If you work in particle physics, this kind of thing happens all the time in particle accelerators. Like particles with a really short lifetime live a lot longer as they are kept in the synchrotrons. So this is kind of trivial matter now. Moving rulers are harder. We don't have any spaceships that move at relativistic speeds. But I'm still claiming that moving rulers don't appear short. They are actually short. So we have corrected for any trivial effect from the travel time of light. After having done all that, these are the real effects that remain. So, whenever I say the word observe, that's what I want you to understand, that we have already made those trivial adjustments. And whatever remains is the, property of the universe we live in, space-time we live in. It's the actual real property of the nature. It's not just some artifact of, it takes light time to travel. And one other thing I want to note is, even though we are going to be using light to illustrate a lot of these things, none of the special relativity is actually specific to light. It's the property of the space-time itself. So gravitational waves, which you recently heard got detected, also travels at speed of light because gravitational waves also move through space. When we get to, maybe when we get to quantum mechanics, essentially any particle with a zero mass will travel at speed of light. So, sorry, that's a little bit too far ahead. So even though we are using light as an example, because it's a convenient example, what we are talking about is the property of the universe itself, not any particular one example.
Having good intuition for properties of gamma and beta is useful not in just writing down Lorentz transformation, but also in answering various questions that relate to relativity. There's really a reason we define these parameters. Let me start out with the beta, even though it's not the first thing we define, so that I can use beta for the other definitions. So beta is defined as the speed at which something is moving, v divided by c, speed of light. Both of these quantities are that people have experience measuring. And given this beta, you can write down the gamma factor, which is 1 over square root of 1 minus beta squared. I just have this memorized. And the question says they are useful in writing down Lorentz transformation. And they are. But what I want to show you is that it's not useful just for that. It's useful for other things. And I think the full application of this, it's easier to see next week when we are going to be dealing with relativistic energy and relativistic momentum. Because what you're going to see is that relativistic total energy, it has this really simple expression That it's not something complicated like 1/2 mv squared or 1/2 mv squared plus mgh. All these terms that you have seen in classical mechanics, it turns out they are much more complicated. Maybe not much. They are more complicated than the relativistically correct expression for total energy, again, which we'll cover next week. That's given by gamma times the rest mass times c squared. That's it. That's our total energy. And the relativistic momentum will be gamma, same gamma there, and times m times a v velocity. So you can kind of see the hint of the non-relativistic approximation here. It's a little bit harder to see here. I'll leave that for next week. But for now, what I can say is that there's a really intimate relationship between energy and momentum, which are very important dynamical quantities, and gamma, and here it's written as mv, but I can write it out this way: gamma times m times beta times c, that's speed, and then whatever direction the particle is going. So when you look at gamma and beta, there's a quite intertwined relationship. So we'll get to that next week with the relativistic dynamics. Think for the remainder of today, want you to have some number sense for beta and gamma, which are described this way. But I think when you're trying to get a number sense for these quantities, it's useful to have these three different expressions, which I will numerically plot, so that we can start to gain that number sense. So one quantity is gamma, and I guess we can write it in terms of beta, 1 over square root of 1 minus beta squared. So that's what we had before. And we can solve for beta in this expression. I've done that before and got square root of 1 minus 1 over gamma squared. That's sometimes useful. Well, let me leave it here and show you some numerical plots to maybe try to gain some intuitive feel for this. There are some properties that's good to know, and you can kind of see them here. With this expression, it's not immediately obvious, but maybe you remember trivia like this. Speed of light is the universal speed limit. If you know that as something that someone who understands a little bit of modern physics should know, then great. What this means is that v is less than or maybe equal to c. And putting in this relationship here actually gives you this relationship that beta is less than or equal to 1. Because v could be c, in that case it'll be equal to 1, and otherwise it's less than 1. And if we're talking about the absolute value of beta, as in the speed, not velocity, then this is, of course, also greater than or equal to 0. So that's one thing that puts constraints around the beta. Once you see that, then you see the constraints around the gamma as well. Imagine plugging this in. When you put in 0 for beta, then I have 1 minus 0, 1, square root of 1, 1. So we get 1 as the smallest value that gamma might take. This is when beta is equal to 0. And in terms of upper limit, I hope you see that as beta approaches 1, not when it's equal to 1, because then you're dividing by 0, but as beta approaches 1, you get this. 1 minus a number ever getting closer to 1. So it's a very small number. Square root of a very small number is still kind of small. 1 divided by that small number is large. So this gamma has no upper limit. So as beta approaches 1, gamma will approach infinity. And that's what you would see on a plot here. Let me see if I can plot this. So your textbook kind of has a version of this plot. Let's see. So let me declare my variable, beta. And I'm trying to plot gamma, which is 1 over square root of 1 minus beta from, I don't know if I remember the syntax. Beta going from, I think 0 is fine. I don't know if I want it to go to 1, 0.9 maybe. What does it plot? If it doesn't do something reasonable, I will look up the syntax and yeah, okay. So this is what it plots. And for this plot, I stopped it at beta equals 0.9, and it maxes out at 3 point whatever. But I'm not limited to that. I don't have to stop at 0.9. I can go to 0.99. Then gamma maxes out at around 10, but I don't have to stop at 0.99. I can go another 9. And I hope you are beginning to see the pattern here. So as beta approaches 1, this will be approaching a vertical asymptote. So beta will never, for massive particles, beta can never equal 1. And as beta ever gets closer, ever infinitesimally get closer and closer to 1, your gamma will increase without limit. So let me just do one more and one more. So at some point of a scale of gamma, it's like all these are so small compared to this that it's basically 0 or basically 1. And let me just put many more 9s here. At some point it'll complain, I think. But yeah, I think I messed it up. I don't know how it's plotting, but I think I don't have enough samples for that. So, anyways, so yeah, that's how gamma depends on beta, and this relationship is a bit. At some point, it's a bit pathological in that it's not very well behaved. I mean, normally when you look at numbers like 0.49 and 0.59, we are used to thinking of those as two basically same numbers. They are basically 1. But when you are looking at the value of gamma, whether it's 4 nines or whether it's 5 nines, actually has a big difference. So it's I guess that's what I mean pathological. They are not well behaved. What you will see much better behaved is beta in terms of gamma. So let me plot beta as a function of gamma. So I'm going to, let me declare variable gamma again. And let me just plot square root of 1 minus 1 divided by gamma squared. Oh, wait, sorry. When I was plotting, when I was plotting gamma, this should have been squared. And what that'll do is that actually makes it even worse because, wait, does it make it worse? I think it makes it actually slightly better because this thing that I had before, if this is squared, then it's slightly better behaved because, well, not that much better behaved. Yeah. So note that missing square from previous results. But in terms of the qualitative behavior, that square doesn't actually matter that much. Let me plot beta as a function of gamma. So beta as a function of gamma goes as square root of 1 minus 1 over gamma squared. and gamma is, this is where I have to be careful. Gamma starts from 1, and let's say gamma equals 10. That's actually quite relativistic. That's where there's a factor of 10, time dilation or length contraction. This is the behavior you see, and I think in some sense this might not look all that well behaved, because as you plot bigger and bigger gamma, in comparison to that scale, this looks like a very sharp corner. So, other than it's a sharp corner approaching horizontal asymptote, maybe where this beta as a function of gamma is useful is, so, at very high gamma, you can basically treat beta as equal to 1. That itself is, I think, useful because in that limit, so, whether I'm comparing gamma going up to 50 or whether I'm looking at gamma going up to 100, the kind of the amount of precision I keep in gamma, it doesn't get worse. I actually, when I specify gamma with 2, 3 significant figures, I actually know beta much better than 2 or 3 significant figures in terms of the number of nines. Where it's actually interesting is in the small gamma limit, as in where you have gamma that's close to 1. So maybe gamma plus 1 times 10 to the power of minus 2. Or maybe even smaller than that, 10 to the power of minus 5. So this would be like a non-relativistic regime. And that's where you see this kind of a nice-ish relationship between gamma and beta. It's so as gamma increases tiny bit over 1, your beta goes from 0. If this reminds you of kind of rotated around the parabola, that's because it is. Because the gamma factor will relate to kinetic energy. And as you might remember, kinetic energy goes as 1/2 mv or m beta c squared. So this is the kind of the low speed version that's showing that correspondence with the non-relativistic results that you are familiar with. So yeah, I think I just wanted to talk about these relativistic parameters, gamma and beta, and their numerical properties, because having this sense of intuition about their numerical properties will help you when you work through relativistic dynamics, and you will see some algebra tips later on that actually relate to these later on, as in next week. But in the meantime, I just want you to bring some attention to these two relativistic parameters that you will see a lot as you work with relativity, and it's worth developing some sense of intuition.
In this lecture, we will talk about relativistic momentum and energy. Now, full disclosure, you can almost consider this to be an optional lecture. Now, this does cover what's in the last two sections of the textbook, section 13.6 and 13.7. But when you look at the homework questions that you will see this week, you will see there are no questions that directly address relativistic energy and momentum. So what I'm going to talk about in this lecture, you won't need to know any of it for homework, but I thought it would still be interesting to kind of wrap up this discussion of special relativity by looking at its application to dynamics. And relativistic energy especially will play some role when you look at nuclear and particle physics. So one important place to start is the reminder of the gamma factor. This is the same factor that came in when we were talking about time dilation and length contraction and all those relativistic effects that you saw by considering the postulate of special relativity. It's a mathematical expression. This gamma factor, it goes as 1 over square root of 1 minus the speed of the object squared divided by c squared, the speed of light. Or as you have seen me write in other lecture sections, you can write it as 1 over square root of 1 minus beta squared, where beta is the speed that you measure as a fraction of speed of light. I like this notation because it makes things look a little simpler. And I think one of the lectures covered the kind of building number sense intuition for this gamma factor, because when you plot it, what you will see is that this gamma factor will go from value of 1 to basically approaching infinity as the speed of the object goes to c, and speed of any object will never exceed c. This won't ever happen. You will see this gamma factor as we look at relativistically correct expressions of energy and momentum. So let's start out with the relativistic momentum. This is the kind of the question that people first learning about special relativity will naturally ask. So you have been told that as an object, let's say of mass m, moves, that its a speed, I guess we are using letter u for now, that this will never exceed the speed of light c. Then the natural question one might ask, does that mean momentum, which we are used to seeing as mass times velocity or speed, is this never going to be more than mass times c? It's a good question to ask, and the short answer is, when you use the relativistically correct expression, no, it's not never, it's gonna be, momentum can increase without limit. Because the relativistically correct expression for momentum is gamma times m times the speed. Yeah, m times the speed, the most it can be is m times c. That's the kind of ultra relativistic case. But as the speed of the object approaches c, gamma can basically increase without limit, approach infinity. The actual momentum, gamma mu or v, can approach infinity. The more energy, the more momentum you put into an object, it'll just increase. So I hope that feels intuitive. If you imagine an infinitely long road and you have a car that's accelerating along that infinitely long road forever, you feel like each second as it accelerates, that it should be gaining momentum, that should never stop. And that is the case in special relativity. Now, as you start to approach the speed of light, from your perspective, it won't be moving any faster than light, but it'll still have more momentum. And that leads to energy. Now, the whole derivation for this relativistic energy expression, it can be, well, this is something that we actually do in calculus-based physics class. We actually don't jump to this, what ends up being a really simple expression eventually, E equals gamma mc squared. By the way, this is where that famous E equals mc squared comes from. That's technically about the rest energy, not the total energy. That's the simple expression. We'll get to it. In a calculus-based physics class, what we actually do first is we derive this kinetic energy expression by using the work kinetic energy theorem. I think we mentioned it before. Work kinetic energy theorem, which basically says that any change of kinetic energy comes from work done. And with the special relativity, with the fundamental properties of space and time not being quite what we thought it was, basically these formulas have to be rederived. Before considering this, we could derive the classical expression that kinetic energy is 1/2 mv squared, which actually could be rewritten as the momentum squared over 2m. We can't rely on that anymore, so we have to do the derivations from scratch. And to just sketch out what we have to go through is we use the fact that force is defined as rate of change of momentum. And this is still the case. This definition still holds in special relativity. We just have to be sure to use the correct expression for momentum, which is the gamma mv. The force is the time derivative of gamma mv, the relativistic momentum. And a work is still defined as the force dot product with the displacement. So we still use that. And what's the challenging part here is that I guess before constant force meant a constant acceleration. Now it doesn't because of this pesky gamma factor. So the whole calculus step of going through it, it's a little bit more involved, so we won't go through it. But the result actually turns out to be pretty simple. So when you go through this derivation, do the integral and all that, and say that work done is your change of kinetic energy, and you start from your at rest state, then you get this expression for kinetic energy, which looks like a gamma minus 1, okay, a little bit weird, times mc squared. Or let me just rewrite this a little bit. This looks like gamma mc squared minus mc squared. And I want to draw a comparison here. When we are looking at the non-relativistic kinetic energy, this 1/2 mv squared, this looks complete on its own. Like no one would look at this and think something is missing or there's anything beyond that. But when you look at the relativistic kinetic energy, this suspiciously looks like it's two things. As in, there's this one thing, and there's this second piece that doesn't look like it's part of one thing. It looks like what we are saying is relativistic kinetic energy is this one thing minus this other thing. And this is where someone, a theorist thinking about this, could have this brilliant idea that this is the actual total energy. And what we are subtracting out to get the kinetic energy from, that maybe the energy that you always have, even when you are not moving. So this is what you might call rest energy. And that consideration having gone into is what you are seeing described at the top here. The relativistic energy, the total energy, is this expression. Relativistic total energy is gamma mc squared. And when something is at rest, then gamma, which is 1 over square root of 1 minus beta squared, something being at rest, beta is 0, so this becomes 1 at rest. So with the gamma being 1, that is the rest energy. E naught, when speed is 0, energy with the gamma 1 is just mc squared. That is the rest energy. And what we call kinetic energy is what you get when you take the total energy, gamma mc squared, and subtract out the rest energy, mc squared. So yeah, that's the quick primer on relativistic momentum and energy. And this relativistic energy is a really large amount of energy. As you can see in this infographic here, it says the power, but it's really technically the energy, because, power is energy per time. The energy of 1 gram is 9 times 10 to the 13 joules. So 10 to the 9 is giga, 10 to the 12 is tera, I think. So it's 90 terajoules. It's such a big amount of energy that we don't really think about that much. It's, from 1 gram, it's roughly twice the energy released by the Hiroshima atomic bomb, which was like 20 kilotons, some number of kilotons of TNT. So yeah, and this table is just showing how the classical calculation differs from the relativistic calculation. So if you have an electron that's only moving at like less than 90% of speed of light, classically you would think it has kinetic energy of 0.251 MeV. That's, I guess, if you somehow believe in the rest energy, that's it's half its rest energy. But this seriously underestimates how much energy it really has. I don't think this number is right. If gamma is 7.09, then let me calculate the correct value of speed here using that gamma. Yeah, so this is a typo. It's meant to be 99. So it's pretty fast, 99% of the speed of light. Again, the classical calculation would say 0.251 MeV, but relativistically correct calculation using this gamma factor gives you 3.11 MeV. And then for total energy, there's the rest energy, which is I think 0.511 MeV for electron. Now, one last thing to wrap up this discussion. So you see the numbers here using electron, which is light, but it does have mass. So all these expressions that you see here, they make sense in the context of an electron. As in, mass is not zero, and electron never moves faster than speed of light. It always moves a little bit slower, like 99% or 99.9% or 99.9999999%, but never exactly 1C. Someone could ask this question: what about massless? That is, m equals 0 particles. And we have examples of those. We've mentioned the photon. I don't know if I mentioned this when we were in quantum mechanics. Mass of a photon is 0. That actually kind of goes with speed of a photon being equal to c, speed of light. It's always moving at c. For massless particles, you might look at expressions like P equals gamma mv and E equals gamma mc squared, and all these expressions kind of break down because for as m goes to 0, gamma is going to infinity, and I guess v going to c isn't really a problem. That's a finite number, but if you have something like infinity times 0, and that's mathematically challenging. So I want you to show you a slightly different expression that is still equivalent to this, and this particular relationship will continue to hold for massless particles like a photon. Takes a little bit of algebra, but I don't think it's too much algebra, so let me just write it out. I want to calculate this combination, which is E squared minus P times C squared. Just a combination, nothing stops me from plugging in these expressions and just seeing what that looks like. So this expression equals, let me plug in the expression for E, for the moment assuming this holds some value, gamma mc squared, whole thing squared, minus gamma mv times c, whole thing squared. Let me distribute the squares, then it'll look like gamma squared, m squared, c squared squared, so c to the 4th power, minus gamma squared, m squared, v squared times c squared. Now, these two terms have a lot of common factors. So let me factor out some of those common factors. I'll factor out m squared first, and let me actually factor out c to the 4th power. And you might be looking at this and wondering if I can do that, but just follow along with me here. And I've factored out gamma squared. Okay, I think I'm done factoring out everything that can be factored out. Then out of the first term, I have just 1. I factored out everything that's there, I get 1. Minus, out of the second term, I actually factored out, oh wait, I didn't factor out v squared. So I have v squared. And then I factored out 2 extra factors of c. So I can express that by v squared divided by c squared. Then when I multiply c to the 4th power back in, 2 factors cancel out, and I get c squared back. So this is the expression you have, and you might look at it and think, oh, that looks so complicated, but watch. Because this gamma is 1 over square root of 1 minus v squared c squared. What that means is gamma squared. What we have here, this factor here, that is 1 over 1 minus v squared over c squared. It's the exact same thing that I have here, except on the denominator. So these two things cancel out. And the final beautiful expression that you end up with is simply, let me write it this way, mc squared, the rest energy, squared. So this is what you might call energy momentum relationship, energy momentum mass relationship. Let me write it out here. E squared minus pc squared is equal to mc squared, the whole thing squared. What's beautiful about this relationship here is that, okay, it does depend on m, which is nice because that means it can be used for things that do have mass. You can use this when m is not equal to 0. Let me move this a little bit. On the other hand, suppose that m were 0. If m equals 0, then you get e squared minus pc squared is simply 0. There's nothing wrong with that, or if you might even simplify it a little bit and say e squared is equal to pc squared, or since you are scaling both sides, you could even get rid of those squares. Say E is equal to PC. And this expression holds for massless particles. We are not multiplying by 0, we are not multiplying by infinity. It's nicely behaved. And I think I did mention this when we were doing quantum mechanics. Photons carry energy, and you can relate the energy of the photon to its momentum this way. Energy of photon is equal to the momentum of the photon times c. So this is how we handle massless particles. This was a question that we frankly couldn't answer in classical mechanics. I don't think there was any way to assign momentum and other properties to a massless particle. But in special relativity, we can. And we can build it in a way where it's all consistent with this expression that holds even for massive particles. And we can treat the dynamics of massless particle like a photon, how it interacts with a massive particle like electron. And in calculus-based physics class, we do more examples and go into more depth about that. But here in this optional lecture for conceptual physics, we'll just wrap up here, mentioning all these dynamical details that we don't quite have enough time to explore fully, and you won't see any homework questions on that. But this is what the special relativistic things that we covered this week, what they kind of add up to when you look at how things that are moving close to speed of light interact. Thank you. Bye.
Okay, so let's get started. So skipping the non-calculation questions. Here's the first calculation question. It says, check your intuition and understanding of principle of relativity. Suppose that speed of light, if you're in a pressure cabin, flying at 320 meters per second relative to ground, when you hear someone speak in the airplane, what is the speed of their sound? Well, let's read the hint. Constraint experience, blah, blah, blah. And all of that comes down to it's actually 340 meters per second. It's a question of reference frames, which you can read about in section 14.1. The textbook, I want everyone to read it. Please read it. It's the question of frame of reference. And if you're using the airplane as your inertial reference frame, in that frame where air is moving with you, the regular laws of nature hold, the speed of sound doesn't change from where on the ground. Now, the one interesting thing about this particular setup is that that you have a medium itself that's moving relative to another reference frame. So if you are standing on the ground and observing the sound waves in the airplane, then you will see those waves propagating at different speeds relative to you on the ground. So sound wave propagating forward will be faster by this speed here. So it'll be 340 plus 320. It'll be 660 meters per second. The wave propagating backward will be slower by this amount. So it'll look like it's moving forward at only the sorry, I guess it's still moving backward at only the speed of 20 meters per second. This is kind of a relative speed calculation. It comes naturally to certain people. To some people, it doesn't. Hopefully, this description here in the hint makes a bit of sense. If not, yeah. It's this is there just to kind of give you a check on your intuition. There's a lot of special relativity that's not intuitive. So if you don't get this, not that big of a deal, because it turns out this intuition doesn't work in special relativity anyway. So let's move on. Question 4. Okay. Check your understanding of the postulates of special relativity. If you're suppose you're on a spaceship moving at half the speed of light, someone fires laser beam within the spaceship at the speed of light. So this question is the light version of this. So all right, within the spaceship, so you would say, all right, speed of light didn't change, so it's one speed of light. Got it? Okay, part B. Suppose that someone else on Earth, not moving in the spaceship, is able to observe the same laser beam. So that's once again the. Oh, I don't know if it doesn't say. Okay. If you look at that other question again, it's kind of that part light version of the part B question. That's what range of speeds of the light does the Earth observe? And here, I guess that this is kind of a trick hint in that it might have led you to ignore this. But this is really what I want you to review and understand. Section 14.1, Einstein's postulate. And this is the unintuitive postulate of Einstein. The first postulate is very intuitive. It's, yeah, so let me not dwell on that. It's the second postulate that's not intuitive. And it leads you to say things that you would say intuitively, I don't think that's true. And what I would ask you to believe is, well, rely on it being true, because it's been extensively tested experimentally, and people have verified it over and over that it's true. And the second postulate is the speed of light c, that's the speed of light in vacuum, is a constant, independent of the relative motion of the source. That speed of light is constant. It doesn't change regardless of what situations you change. So going back here, if you are being tricked, you might be tempted to answer something like 1.5 and 0.5 here. It'll be wrong. They will both be 1. This is what I mean. Special relativity is not intuitive. On the other hand, the answers are much simpler than the intuitive answer. So I guess this wasn't really a calculation question. I wasted like 5 minutes on this. But, I think this was actually good to cover. Yeah, let me move on. Question 5, not a calculation question. Question 6, calculation question. Okay, so this is practice plugging in numbers. And this is what I would recommend, that this is kind of a complicated formula. It's really easy to make a calculator mistake as you're plugging in those numbers. So I guess you could use Wolfram Alpha. If you're not using Wolfram Alpha, what I would recommend that you do is do this calculation on a calculator step by step. So this number here is basically V over C. So let me start out with that. So I'm going to start with just taking square of that V over C. So 0.001 squared. That's V over C squared. Good. All right. So that number there, put it into memory. I think that's how memory works. You know what? I actually don't know. Let's see. 1 minus memory recall. Okay, good. Okay, so that's the number that goes under the square root. All right. Let me put that into memory. Then I guess I actually didn't do that. The next step is taking the square root. So let me take the square root here. All right, that number there. Let me put that into memory. And the very final step in calculating gamma is 1 over that number. So 1 divided by that number I put into memory. Recall that. There. Okay, so that's gamma. Oh, and yeah, there's this instruction, make sure to put in significant figures, because this is pretty close to 1. And for this particular question, I put in enough of tolerance that if you just put in 1, it'll tell you it's wrong. Because I put in a more stringent tolerance than usual. So let me put this off to the side. So you have to put in 1.000, 3 more zeros, 0, 0, 0, 5. And after that, it should be fine. So it's correct. Yeah. So if you're using your calculator and if you're getting the wrong answer, what I would recommend that you do is check with Wolfram Alpha. So now, if you're using calculator, once again, this is the order I recommend that you go in, just inside out. First, start out with a ratio, 0.5 for part B. Square that. That's the V over C squared, or V squared over C squared. Put that into memory and do the calculation of 1 minus that number, 0.75. Take the square root, put that into memory, and take the reciprocal, 1 divided by that number, and that's gamma. So 1.15, that should be close enough. 1.15. Good. All right, let's do C. Now C, so here I'm plugging in, even though each question is follows the exact same steps, I'm doing all of them because you have to watch out for different things depending on what regime your number is at. Part B is actually the easiest one because you don't have to worry so much about tolerances and significant figures. In A, you have to make sure that you put in all those extra significant figures for gamma. For C, where you have to be careful is, I gave it. Be sure to use all the 9s. Missing a single 9 could result in a large error. So, I mean, you can try that on your own. So here, let me just do that. So I'm going to start out with V over C squared. So it's 0. Let me count that. 9. Okay, 4 more 9s. 1, 2, 3, 4. Okay, that's the given V over C. Square it. Put that into memory. 1 minus that memory stored number equals that. Take the square root. Put that into memory. 1 divided by the number in the memory. That's the gamma factor. 7071. So it's a very large number. 7071. Okay. All right. So that's one calculation example. It's I give you the formula, and all you have to do is plug in the numbers. Question 7. The Lorentz factor is actually, and here is where Try some calculation below. Part A is the one that I'm not sure if you can even do that on a calculator. Let me try that on my calculator. How do I do this? So I already derived the formula for V over C for you. It's a square root of 1 minus 1 over gamma squared. So let me get my calculator out. Let me do 1 divided by gamma squared, which will be parenthesis 1 plus, 1 plus this super tiny number, 5 times 10 to the power of 15, close of the parenthesis. Wait, I need to square that. So that's 1 over gamma squared. Wait. Yeah, that's 1 over gamma squared. Well, equals. Right. That is 1 over gamma squared. Let me put that into memory. 1 minus that number in the memory. Take the square root of that. That's my V. Something that's very close to 10 times 10 to minus 8. So I guess that's 10 to minus 7. Well, it doesn't. So 10 to minus 7 in the scientific notation here is 1e minus 7. All right, I guess calculator on the Windows computer can do that. Good. You can also do that on your on Wolfram Alpha if you get issues with getting that. Okay, let's do. I'll do parts B and C too. Let me do this a little bit more quickly. I need to leave soon. So I started to 1 over gamma squared. It's 1 divided by gamma 2 squared. That's 1 over gamma squared. Store in the memory. 1 minus that number in the memory. Square root it. And wait. That number is not right. That is weird. It subtracted the minus 0.25. Is there a way I can? Well, let me just do square root of 0.75. 0.75 square root it. That is weird. Let me just not press the equal sign. No. 0.75 square rooted. Okay, that's the correct answer. 0.866. I don't know. You should always be familiar enough with your own calculator so that if you do something weird, then you can notice. Speed corresponding to gamma equals 12. All right, I'm doing the same thing again. 1 over gamma squared. 1 divided by gamma squared. Yeah, that is 1 over gamma squared, stored into memory. 1 minus that number in the memory equals that 0.993. Sounds about right. And I need to take the square root of that number to get me, I guess I won't press equal sign this time. Get me the V over C, 0.99. Let me put in 65. 0.9965. All right, that's it. Okay. I think I have some more calculation questions. Let's see. All right. So you should read the section 14.2, which will give you the time dilation formula. And the time dilation formula says that if we have something taking some amount of time, tau or delta t naught proper time, read through that, please. If you have something that takes delta t naught in its own rest frame, then the amount of time it takes in another reference frame where the thing is moving is the dilated time. That's the Lorentz factor times delta t naught. So this is the little thing I was trying to skip. The one big part of doing this calculation to figure out what the dilated time is, first figuring out what the Lorentz factor is. That's the exercise we had to do for question 6. So when you're doing question 8, a big part is, well, doing the exact exercise you do in question 6. So let me do that for part A. So I have a V is equal to 0.5 C. So I need to write down what the Lorentz factor is here. So write it down for yourself. That the formula for Lorentz factor is 1 over square root of 1 minus V over C squared. So I'm just gonna plug in these numbers into calculator very carefully. So let me do that. So I have V over C, 0.5 squared, put that into memory, 1 minus the number in the memory equals 0.75, take the square root, 0.866, put that in the memory, 1 divided by that number in the memory. That's the gamma factor. Now, from the time dilation formula, what you know is that the dilated amount of time, t, is equal to the gamma factor times the amount of time that it takes in the rest frame. So here, the time is 1 microsecond, so the time here is just going to become 1.155 microseconds. Now, if this number is different from 1, as that'll be the case for most of you, make sure to take this number and then multiply it by gamma. So don't put in just the gamma here, 1.155. Here, parts B and C are very similar. You'll just get larger numbers, but you don't really have to worry about stuff. All right, let's keep going. Question 9. Good. So from the perspective of Alice, Bob is moving towards her at 0.8 C. And there's the thing about velocity addition, how this is consistent with this. And I'll just leave you at, you don't need to worry about it. The velocity addition formula is a super complicated formula. I wouldn't really worry too much about learning that formula. I'm pretty sure I'm not going to be asking you about, asking you quantitative questions on velocity addition formula. I'm like 90%, 95% sure. So here, really the thing that you should be aware of is you have these two different numbers, 0.5C and 0.8C. What number should you use? The number you should use is 0.8C. Because when Alice is doing the measurements, Alice is at rest in her own frame. So with that, you also should know length contraction formula. Read the section, please. And when you read through the length contraction formula, what you get is that length of a thing measured in a frame where it's moving relates to its length in its own reference frame through this. It's the length in its own rest frame, what we call proper length, divided by gamma, or times the square root of 1 minus v squared over c squared. Let me use this one. That's probably more direct and possibly a little bit less calculator number plugging in. So the length in the reference frame where the ruler is moving is equal to its proper length times square root of 1 minus v squared over c squared. So here v over c is 0.8. So 0.8 squared, put that into memory, 1 minus that thing in the memory equals 0.36. Take the square root of 0.6 again. So that's my 1 over gamma. Multiply that to the meter stick. So it's a meter long in its own reference frame. So multiply it by 1. So in Alice's reference frame, Bob's meter stick is moving. So she'll measure it to be shorter at the length of 0.6 meters. Now, because I'm very familiar with Lorentz contraction, without doing the calculation, I know this to be 0.6. And I guess you think about it on your own, see how that makes sense. Let me just leave that there. I think I have an essay assignment on these relativistic paradoxes, which I hope will give you some more intuitive sense for how these two answers can both be right. Okay, let's look at question 10. Oh, by the way, this one I know the answer to that. Second postulate of special relativity. So let me just do that first. Okay, good. So part B is actually easier calculator-wise. So let me do part B first. So you have relativistic kinetic missile, which is moving at 90% of the speed of light in the reference frame where it's fired. But the thing that's doing the firing is itself moving at the speed of 0.5 c. So pay careful attention to the symbols of V and U prime and make sure you match how you are plugging that in here. So I'm just going to start out with this factor here. So I have V 0.5 times U prime 0.9. Actually, it's 0.5 C times 0.9 C. So when you divide it by C squared, you just get rid of the C's. Add that to 1, so plus 1. Okay, 1.45. Let me put that into memory. And I need a numerator, V 0.5 plus U prime 0.9 equals 1.4, that's bigger than 1. Divide that by the denominator, which was stored into memory, so memory recall equals 0.9655 C. So let me put in 0.9655. And that should be the correct answer. Yeah. And this is how this velocity addition formula kind of makes sure that the consequences of special relativity are enforced. So the speed of this projectile, no matter what reference frame you are at, it's always going to be slower than speed of light. So you know the speed of this kinetic missile at the reference frame of the target was not 1.4 c. It was, well, after going through the formula correctly, it's only 0.9655 c. Part A, I guess you could go through all this calculation, or kind of reading ahead here, you could cheat and use your common sense in Newtonian mechanics and just to do this plus that, which will give me 0.0000002. Now, if you actually plug in the numbers, it'll be a little bit off from that, but I think that'll get graded as correct. Now, if you want to practice, plug in the numbers. Just be careful with significant figures and just how tiny the numbers are.